welcome to, I guess, the first time that Partisia is talking on a workshop with Secret Network. Today I'm going to be talking about the synergies of MPC and TEEs for DApps. But before, I'm going to give a little bit of a background about me. So my name is Bettina. I've actually been in Partisia for 3 months. I am the head of engineering and AI and I guess relations as well. And I'm pretty passionate about pets, I'd say. Like generally, I've been doing research. I was doing research at Imperial College before, specifically in like zero knowledge proofs and how you can apply that to self-sovereign identities. And that's where, like, I guess my love for like data privacy and specifically when applied to distributed ledgers came from. So a bit on what we're going to be talking about today. So first, I'll just do like a small introduction on what MPCs are. And I guess most people here will know what TEEs are, but I'll still do a little bit of like a small analogy. Then I'll go into, the synergies between them and why I think it's like so cool to kind of put both of those technologies together. A couple of the use cases that I personally find the most exciting. And finally, I'll have a little workshop on how you can get set up with MPC, and then you can, start being creative on how you can then apply it with TEEs at Secret Network as well. And we can do a little Q&A at the end. So let's get into it. I'll explain first a little bit of an analogy of what TEEs are. So as you might know, it all works through like a encrypted enclave. This enclave, you can imagine it as a vault inside of a bank. So, inside of a bank, everyone might know what's going on outside. Like people are walking, there's like, loans being given to people. But inside of that vault, like no one knows what is going in. And like there can still be like transactions of money and like money movement inside of that vault, but no one really knows what happened. But you still got a registry of what money went in and out. So that's a little bit of how like you could imagine a TEE like work, where like it is just a kind of its own little enclave inside of like a computer where you can do different types of computations, but all of those computations will stay encrypted in that enclave. And then we can go into MPC, which I guess is more of my land. And I will explain it more as like, so obviously multi-party computation works in a pretty different way, where it's more like you'll have a number of different nodes that are communicating between each other. Each one of these nodes will actually run the computation on completely encrypted data and will also compute in an encrypted manner. And it's only really the result of this computation that is publicly available to everyone. So we can give an analogy for this as well to maybe like imagine it more visually, which actually helps me as well. So imagine like you're in a group of friends and each one of you has like a really special puzzle piece, and you don't want to know like how your piece is really cut. It's a special, like, let's just imagine your piece is cut. Now you want to put all the pieces together to create this puzzle, but you don't really want to communicate between each other on like how to put it together. So you're going to run the computation of putting the puzzle together in a encrypted way. And the output, which is like the puzzle, the image, will be publicly available to everyone without really knowing how the pieces came together. And so how do these two technologies like even work together and how they can enhance each other? So there are some things with TEEs and MPCs that can really kind of get some help from the other one. For example, how MPC can enhance TEEs. There is one thing with TEEs that you kind of need to trust the kind of hardware provider to basically, be trustworthy enough and don't like add any potential like points of failure. So one of the things that MPC can mitigate here is that, let's say one of the nodes running like a TEE ends up being like vulnerable, or someone tries to like hack it some way, which is pretty complex, but it can happen. MPC would allow for the network to still be healthy and the nodes to basically talk between each other without, really kind of having to trust anyone really. So it kind of really makes the whole system fully trustless. I guess on TEEs boosting MPCs, there's a lot of really cool things. I think specifically the one that is the most fun or interesting one for me is how TEEs can boost a lot of the MPC computations. Like obviously with MPCs, you're communicating with all these different nodes to run this encrypted computation. And obviously when you communicate between each other, that is latency, right? You need to, like, it takes some time to get from one node to another, specifically if you need to run a computation in different loops. That, if you can imagine, is specifically what happens with AI. So TEEs can really boost the performance here to run things on like a near native. And when I mean that, like if you were running on a normal computer without any encryption, it's almost like near native time. So, you can run like, I guess, pre-processing of certain computations on TEEs. And then maybe sometimes you actually need a network of different people adding encrypted data without like, and then it really depends on the setup. And I created some diagrams, so it's actually a bit maybe easier. I appreciate my diagrams. I like to do them on my computer. So this is normally like, simply speaking, how a data flow from TEE to MPC would work. So let's imagine we have like a user, a decentralized application. We can imagine this being like something with, imagine you have a D app with like hospitals, like a network of hospitals in a country, like talking to each other. They have this little UI and each one of them needs to like send encrypted data. Let's say it's like X-rays of like tumors of a lot of different people. And obviously this is pretty sensitive data. So what would happen is, for example, like you would connect that to the secret network, like a secret network TEE node. And so the node would receive the data in a secure manner. It could pre-process it, filter. So let's say that like, I don't know, like we need to pre-process those like X-ray data in a way that it is either in like binary format, which is what works best with MPC nodes, or it could be in an arithmetic, like for it to be computed in an arithmetic way, but it still needs to be like kind of translated into numbers, if that makes sense. So obviously that needs some pre-processing, that needs to happen in a completely encrypted environment. And actually the TEEs will be the one that actually splits the data into the different secret shares. And that will be then sent to a Partisia MPC node. Then the MPC nodes could be like running analytics on all of this data. And they could figure out, for example, for research on this, like X-rays on, what are some patterns that are common on specific age ranges or like specific lifestyles. So that's pretty cool. And this is where a little bit of like the computation loop would work. The Partisia MPC node or like cluster would run basically most of the computation. Well, not most of it because a lot of the pre-processing already happened, but some of the computation, so like analytics, let's say, and then those partial results and a lot of these proofs would then go into the secret network TEE node back again. And it would basically translate like probably all of the values from this analysis that are in a very like numeric way into like a final output that they can share back in an encrypted manner, like back to each hospital. So they never have to like ever communicate with each other, even set up anything between each other. So yeah, I mean, you can see it's pretty cool. And this can be applied to different things. So these are like the 3 use cases that I'm most excited about. So AI and privacy. Imagine a model for like federated learning. So you might have a lot of ML researchers, and this one kind of loops into the confidential DeFi one. But imagine you have a number of researchers that, they're training their models in different ways, and they might not want to share like all of the ways that they're training these models. And you can think that maybe that doesn't make sense, but if you think about how OpenAI doesn't really talk to Anthropic or things like that, and how they could probably collaborate, all of these like really big companies, on a lot of their research. And this can be applied to like AI drug discovery and other things like that between universities. You can apply the same model that I just showed before, where like all of these people have different ways of training their models, and that data can be shared between each other, and actually just get like, full analysis and like find different ways where they can actually like collaborate without collaborating, if that makes sense. It's like pretty cool. I think an interesting use case is like investment platforms or DeFi, specifically hedge funds. If you think about hedge funds, I think one of the reasons why we haven't really seen a decentralized model of a hedge fund is because obviously a lot of the models that like quant engineers or quant researchers create have a lot of alpha, and you don't really want to put that either in a public, like on a public like a public blockchain, public repository. And so that would end up meaning that you would have it in a private chain, which then kind of defeats the purpose of having, like a blockchain decentralized system. The really cool thing with like combining both of our technologies, MPC and TEE, is that you could actually create a system where you have investors on one side, you have the alpha kind of creators, which like you either have the data providers or the researchers creating the models. And yeah, these people basically can just upload their encrypted data to a TEE node. You can then basically make a share where like people are putting in like money from different places. This is all traceable, et cetera, et cetera. And you can then finally see the output once you've gone back into the secret network nodes. I'm going through this quite fast, so we need to actually get into like the practical bits. And yeah, I mean, I've kind of explained like how healthcare data analytics can work. There is like, I think this is like an incredible place because you can, again, talk about like AI drug discovery. You can create models where hospitals are kind of like exchanging data between each other, but it can also be data from like insurance companies for people to actually take a little bit more ownership of like when they're going to an insurance provider, they kind of have a bit of your data and they tell you what the price of your insurance should be. With a model like combining, again, MPC and TEE, you could have a way of like keeping your data completely encrypted, but still being able to give enough resources for an insurance company to give you a price, but you know that it is the fully correct price and they're not inflating it in like many different ways. So yeah, I think that's a little bit of me talking. Now I would like to basically introduce you to Jens and Mikey, which are some of my most expert engineers, specifically in Rust. And they're going to walk you through like how you can create your first like MPC computation. And it'll be like a quite simple example on how do you compute average salary, specifically if you have like different types of people in a company and you don't want to share like if there's disparities and things like that. So yeah.
My name is Mike Anderson, sitting here with Jens Schiel.
Welcome, everybody. Well, first, I'm just going to show you the playground very quickly. If you go to the GitHub page for the Partisia blockchain and find the repo, that playground, you will see a quick repeat, which will guide you into how to actually boot it up. I also quickly want to show you if you want to try and code along while we're doing the learning challenges. To boot up a code space, all you have to do is click on the code icon, click here, and create code space on main. It will then set up the code space where it will install all of the tooling needed. It will also give you VS Code editor to edit your contracts. I will be doing the development locally because that's what I'm used to, just using a clone of the dev playground. So now it's booting up. As it is booting up, part of it is actually creating these new keys for you to use on the testnet. So right here, it's not done yet with creating the next key, but you can see here in the account A that we have already gotten our new key, which we'll be able to use.
Just to elaborate a second on this one. Important thing to do anything on the blockchain is to have an account for the blockchain. This account A is a newly produced one that has some testnet coins already on it. So it's just ready to go. It's a plug and play private key. And this is the actual private key you can just use to generate your public key and start getting anything done.
So now I will go over into editor of choice here.
Yeah, so what Jens is saying is that he's taking the DAC background, cloning it down locally on his machine. You can do what Jens is doing and having it locally.
I've just cloned it. So first we have these tutorials for the petition example application. And what it would like us to do is to do the learning challenges. The first one they would like us to do where we are extending the contract is where we are actually setting it so we can only use one of the two accounts to assign our petition. If we go in to the petition contract, we can see here the definition of the petition contract, where we have the state, which is what is on the chain and what is can we change with our different actions. Then we have the init action, which allows us to create the first state of the contract when deploying on chain. This is where we would set the description of our petition, like I like cake, I will definitely sign. And then we will also initialize this sorted set where everybody who has signed the petition would be kept in. So that would be the first state, right? So now we would like to have it so that the only accounts that are allowed to sign is account A and account B. So how would we actually do this? We would extend, one way to do it is by extending our state and holding those two accounts just like this for account A and account B. And now we will have to add that to our initial state. So we can just add them as parameters for our init function, address A, account A, and account B. Right. Now we can just add those two. Boom. And now we just need to assert that the sender of our action when on chain is one of those two accounts that we have set in the initial step. One way to do this is by using a normal Rust assert, where we assert that the context which holds the sender is equal to account A or context.sender.
Yeah, so Jens is trying to achieve just a standard conditional, hey, do we already exist in the state A or B as these accounts that can actually sign our petition?
So how would we be able to check that this worked? Well, one of the ways that we can do this is actually by deploying the contract right from our command line. We have the Kaggle Partisia tool, Partisia contract, where we can first build our contracts and check there are no compile errors also.
Now we're building the contract, we're using the Kaggle Partisia contract tool to build the contract, get the files we need to actually deploy the contract directly on testnet. So we can constantly check that what we actually do works on the blockchain.
So now we can use our command line tool. We can see what the different options are. So what we would like to do is we would like to send a transaction, and then we can see what the different options are here. To send a transaction, there we can send an action, we can deploy, or we can refill with some gas. Now we would like to deploy our petition contract, so we can call the deploy, and if we see the code, well, then we can see that what deploy needs is a public key, a private key that it is using to be the sender, what bytecode file that is. In this case, since it's a public contract, that would be the BASM file, and we would also need an ABI file, where ABI stands for Application Binary Interface. What that actually means is just a way of telling how to communicate with your contract and how to communicate with different parts of your contract. And then we also need to send the init parameters. In our case, that would be the account that we want to be A and the account we want to be B, and also the description of the petition contract. Let's try and deploy. So it is located in this folder. And here you can see that we have our petition contract, ABI, and also the BASM. All right. So now we need to give our initialization parameters. So that's a string where I would like to have my petition, I like the account of A and B. Oh, I've got something. I don't have any accounts since I don't have the code space. So first off, I actually need to do something else.
You need to create an account. So the idea is that the command line tool can actually do a lot of things for us. And Jens is heavily showcasing that if you actually need an account, you can just ask the command line tool to create your account, and that will actually fill it up with gas. So you're just ready to go from the start of it. The way you do it is that you write the CLI account create, and then you can do --help if you want to add some of the options there.
So now we're getting an address for our account A. I will also do this for account B. Let's get gas for it and C. So now that I have my 3 accounts, I can now go back and try and do the deployment of it, where I would like to have that account B and C, let's say account A and B, just not to get any confusing, will be used as the only accounts allowed to sign. Now I just need to specify who will be the sender, and in this case, that is my account. Good. Selection. give us waiting.
So the command line tool is designed around the possibilities of getting help every time you do something wrong.
If I try to sign in with another account, for example, account C, which was the one we deployed it with, if I sign in with my other key here and try to sign it, hopefully. So we can see that we send our transaction. We can also see that it failed.
Yes, so that means the assert has worked. It has not been signed by account C.
Exactly.
It has only been signed by account A in this case. That was completing one objective of the workshop. This is how you could actually develop something. You can build it, you can deploy it, you can get a private account, and all of this is done but from scratch. So what we have with us as the next treat is to actually go in and work with some zero knowledge parts of it. Because the superpower of Partisia blockchain is zero knowledge and MPC, and using that one. And in the tutorial space, we actually have a contract showcasing one of the widely used examples of ours, the average salary example. And that's the next part we'll jump into and try to complete the learning challenge in average salary. So average salary is a contract based around everybody in a company giving in their salary as input, and no one wants to share their salary, but they would love to understand what the average of salaries are in a company without sharing their salary itself. And the first learning challenge is focused around, scroll down maybe a bit, let's jump down to the challenge itself, is to make the zero knowledge computation count how many $0 inputs there are and return that as public available variables. And to kind of say, so if you have a company of 10 people, you would love to understand if 7, 8, or 9, or all 10 of them actually gave input to the salary. So you just don't take an average from a bad data inputs. That's to say. So the first challenge is about understanding how many inputs did we get to the average salary contract.
Yes, so we can also use them later to actually compute the average of those inputs. So if we go here to our average salary and into our contract, the first thing we want to do is, since the number of inputs are always public, this is not a problem. So we can just count up every time we get an input. So here we have the number of employees, but instead we actually want to count them when we actually are getting the input and not just when we are starting a computation. So right now, this number is coming from when we start the computation. Here we are starting our set query computation, where we are setting our number of employees to be equal to the number of secret variables that are currently given to the contract. But instead, we would actually like to be able to calculate the average once again. So that means after we have computed one time, this contract is done. It cannot be used again to compute the average. However, we would like to compute the average every time we get a new employee. So we can add the person to the contract. And then when there are enough new employees and enough of salaries as inputs, well, then we can recompute the average again for our company, and then without revealing anything about anyone's salary, we still know the average salary of our company.
So we're changing it from we know how many inputs we will get,
yes,
to we do not know how many inputs we will get to the contract.
Well, it's more in the sense of we want to use the old inputs again in a new computation.
Yeah, okay, in that sense, yes.
So, great. So how do we do this? Well, first off, we need to have this number of employees to be something that we can increment, and it starts from 0. So instead of an option, we're just going to change it to an U32 integer. So down here in the number of employees from the start, there are 0 number of employees who have inputted anything. Good. So what we want to do now is we want to make sure that our state is updated every time we have a verified input. That means an input that is correctly found that has been sent to our contract. So how do we add it? Well, we add it here into the setk onVariable inputted action. This action is called when the node has confirmed that the input is well formed. So that means not only do we know that they send something correct to our nodes, but we also know that they are following, so we can actually compute on the input and get a correct answer.
And we'll talk a bit more about that when we actually deploy it.
Yeah.
It's more visible to see this in the browser.
Exactly. So first off, I'm just going to add, so it is a mutable state that we're having, so I can actually increment our state. So number of employees is 1. So I am just incremented it, and then I'm returning the state again. So now we just need to check that the number of employees that we actually have are greater than 3. So here we can just insert our state and then use our variable. Now we should count it up every time that we are actually getting an input. So what I want to do here is again,
and then the public available counter there is. So everybody will always be able to see how many inputs, as they also put in the browser itself, how many inputs will be added to the zero knowledge table.
Oh, there's an unwrap I have not gotten. So let's see where it was. It was in.
So as expected, when you develop anything, it takes a couple of tries, right? So that's why it's also to work. And this would also have been something you would have had in the dev playground from the browser perspective. You would also have gotten the help there when trying to build it. So it's the compiler itself that helps you see what your error is and how you could fix it. It often comes with a good suggestion.
Yeah. This is just warnings about me having a mutable state instead. So now I'm just gonna quickly deploy a rich summary contract with this. So I done this account, but again, it's my deploy action, and I'm using just the other keyword for transaction, set KWA, which stands for zero knowledge vessel. That is when it is a zero knowledge contract instead of a public contract. And then our API, and then our public key, which we were using to deploy it, and then how much gas we're sending.
In general, when doing any zero knowledge contracts, you would need to put in a bit more gas because it is a bit more deploy expensive to do. So that's why you see that Jens used a lot of gas as well. Yes. But on the testnet, we have a lot of gas, so that's not an issue.
So this is our contract. Right now, there are no transactions that we can see. However, we can see that I am the administrator. We have our average salary result, which has not been set yet, and the number of employees who have actually entered an input is 0. So if we go back where we have logged in with our other accounts and we search up our contract, we can see, okay, let's try and interact with it. So I would like to add my salary for as the secret input. So let's just say I make about 550,000, let's say that. So we add the salary, and now we can see there is nothing yet, but if we update, we can see that the transactions have gone in. So what we can see here is I send in my add salary, which is the action we can see right here. Add salary, that's the action we call to add our input. What happened then is that we send this input to all of the nodes. All the nodes are now confirming that this is a valid input we sent.
So, and yeah, let's expand a bit on the ZK node. So whenever you do any zero knowledge contract deployment in Partisia, you always make like a contract with 4 nodes to do the actual computation for you. And it's because the way MPC simply needs to distribute the secret shares, so they are on 4 different nodes. And simply by having these secret shares on the 4 different nodes, they need to be connected in a network. You need to give some collateral. In the test case, it's just the test MPC collateral coins. But in the real mainnet, you would have to stake some MPC against the deployment of your contract as collateral for these nodes to actually do any computation. And if any of these makes any malicious attempt to get your data, or they're dropped by doing something they shouldn't do, they will always lose the collateral that you have staked towards your worth of the data. So that's kind of how it works. So every time you send any input, you need to send 4 secret shares to 4 different nodes. So one secret share per node, so 4 secret shares in total. And that's what Jens is talking about, showcasing here. He's added 1 input, it goes to 4 nodes, and it simply needs to do that for us to compute on it in the MPC method.
So now that they have all confirmed it, we can now see that we actually have our first added input. So if we go to the state, we should now have an updated number which says 1. So it seems like that we solved that challenge.
Yeah.
However, this number is public. So if I am making averages based on some private information, something like gender, this would not be allowed, because then let's just say I would extend this with a number of female employees, number of male employees. This number will not be safe anymore, since this is private information about the people who are inputting it.
So yeah, we would have to extend the secretness of the variables we actually put in. So number of employees can be a big enough number that's not saying anything privately about anyone. But if you have a company of the same 10 people, and if 3 of these are females compared to the 7 males, it would be much easier to kind of grab personal identifiable information out of these people in our contract.
Yeah.
So to make sure and ensure we don't give anything out, it's on us as developers of the contract to make sure that no secret information is given to anyone in the system itself.
Yes.
And that's the challenge number 2. Let's maybe grab the challenge and just read it for everybody to be on the same level. So what we need to, in the second challenge, is to add a gender next to the secret input and try to branch by using a secret condition.
Exactly.
And branch means kind of like an if statement, if you understand.
Yeah, exactly. It is saying, oh, if it is male, he should be added to the male sum of salaries, and we increment the counter of males who have inputted 1. But we need to do it in secret.
So no one knows it.
Yeah, exactly. So how would one go about this? First off, we need to define an input type such that we can actually define more than just having the salary as an input. So here in our secret input, we are not defined an input type yet.
So what you could do, as I sent the deployed zero knowledge contract into the chat, is that you could actually go and interact with the contract on the testnet. There are no asserts blocking anyone from adding any input to the zero knowledge contract. And if a lot of the people here actually goes and input something, I think we'll try and compute the average salary, or at least the average imaginary salary of this room here, and no one would be the wiser of who inputted what. But we could figure out what the average of salaries would be here. So if you want to go and interact with the contract, feel free to add anything into the contract, and let's see how many inputs we get.
Yes, so I'm just adding the secret type that we would like to be using. So I cheated a little, and therefore I have already defined how this should look, our secret input. So here we are designating it, but we are actually defining it inside our ZK compute file.
And why is that? Why do we have 2 files now in a zero knowledge contract?
Well, the contract part of it is the public part, the actions where you can interact and where you define how you're handling public information. This is also where the hooks for adding inputs is, and where you can start the computations from. However, defining the underlying zero knowledge computation is done in the ZK compute. So in here, we can now add struct, which will be our input type.
And if you want to sum it up a bit more, the contract versus ZK compute files, the contract is basically what you see in browser, what you interact with, the action you want to change, or if you want to increment a number in the public state. Whereas the ZK compute is actually the instructions for how to calculate anything on any node within our MPC calculation here. So those are the instructions for handling the computations when we ask for it. So they are kind of more the hidden computation that no one needs to understand anything about besides the computation part of it.
So now we have added our secret input. The secret input contains the salary, which was the same as before, and secret binary integer of bit size 32. And we have also added a gender choice of an SB 8-bit integer.
Yeah. Words are difficult.
Now we are defining it to be the secret type that we will allow to be inputted. And we're also saying it here for our input definition that the ZK input is the type that we should use. Now we have defined that we are actually using a different form of input. So over here in our computation, we cannot just read out an SBI 32 anymore, because it's actually not an SBI 32. It is actually our ZK input. So what we will need to do here instead is we will need to define, we will actually need to load our ZK input instead. We have this, and here we could then say reported salary. Let's just say it in salary, so we can actually access the field we have. But right now we're just doing the same as we had before. We're not doing anything based on the gender. now we would like to have some form of structure such that we actually know when we are summing for the males and when we are summing for the females and so on. So we are actually summing for the correct results. So to do that, we can define something like a struct, which would just be our general sums. And in here, we'll just define that we have two fields. We have all of the salaries that have been summed, where there would be 3, 1 for each of our options. And then there are counts of each, how do you say, gendered input you have. So a male count and a female count and an other count.
What Jens is trying to kind of say is that how can we understand what a gender is, which is a very polarized thing to say in these times, but it is to how do we understand it from a programming way of looking at it, right? So we need to understand that a gender could be numbers or something that makes it cheaper to do it. And in here, we're doing it the salary sums and how we can work with that as a struct. A second objective of building the structs into the CK compute is simply that it's just easier for us to code things when we build the structs this way. So we always recommend that you build your structs the same way for contract and ZK compute, because it just makes it easy for you to use the variables that you actually get when doing any CK between these contract and ZK compute, as long as it doesn't, show anything it should.
Exactly. So I have I've just
copied in a lot of stuff. Why did we copy in a lot of stuff?
Exactly. So this is the struct I just talked about, which is defining the sums and the input counts. The sums are salaries summed together.
So the math behind it is taking the male salary and dividing that with the amount of males that has inputted salary.
Exactly.
And that's how we get the average, just for everybody to be on the same page.
Exactly. So now we need to define some everything function, which earlier had the total reported salary starting from 0, then it summed all of it up, and then it just outputted the full sum. Now we need to define the counts, which are starting at 0, and also the sums, which are starting at 0. So how would we be able to do that? Well, we can use a vector for that, for both of them. So here we have our own salaries, and we have our input counts, 3 of each, which are starting at 0. So now we need to branch in the case of genders, such that we are actually counting up in the correct places. So to do that, we need to still check that we have a variable of our salary. Just quickly, a reminder here, not a reminder, but a quick note here is the way we actually identify different variables from each other, the ones that have been outputted by a computation and the ones that are being inputted by people, is that we are using what is called the public metadata of the input variable. In this case, we are designating all inputs as salary variables. The way that's defined is that we can see up here, we have a salary and we have a sum result, which is the public metadata we are sending along with it. So when we are adding an input in our add salary, we can see that we are sending along with the input that's being added, the metadata that it is a salary variable that is being added. Also, when we now that we're here, when we are starting a computation, we can also see that the output metadata is linked to a sum result. So that means that the variable we will output will have the metadata of sum result. That means it will also not be used in a new average when we're using that. So we need to check that the variables we're using are of the correct kind that we would like to have a part of our average computation.
And we definitely need to explain a bit more about this, right? Because what Jens is talking about is that we have some public metadata that you in the contract can define stuff that needs to be publicly available as part of the variables you're putting into a zero knowledge computation. And it is because the nodes that gets the secret shares, they know nothing about the data you're giving them. So sometimes you would like to give some public available information that the zero knowledge nodes they can report on and do stuff with. As an example, it would be saying these results are from this calculation. You do not need to use these anymore, so we can do more of them. And if we didn't tell them about it, the nodes themselves, they would never be able to understand what was the first computation and what was the second computation. So I kind of putting these blocks inside our variables to kind of identify them in a way that we don't share the secret, but we share parts of the computation steps that is part of the contract itself. So it just makes sense that of course we want to know what was the first computation and the second computation. There is no secrets in that. That's just a system choice we need to do. Otherwise, we will not be able to reuse the contract that we're deploying.
Now we need to make sure that we are incrementing the the right indexes in our two lists, because we made two lists here, which has three elements, one for the sum and one for the count of inputs for the gender. So for each variable that we have that is inputted, we would like to have, we are checking that they are actually a salary input. Then we load that input into our type as the type we have defined above. So that means it has two fields, the salary and the gender choice. So now what we can do is we can go over all of the possible choices of gender. For in our case, it is 1, 2, 3. And then we can check if our input's gender choice is equal to this identifier +1. So we are just checking. We're actually asking, are you a male? Okay, no. Are you a female? Okay, no. Are you other? Okay, yes. Great. Let's add your salary and increment the count for others. So that is what is happening right here. We add the salaries and we increment by 1 for the counts. This is all great, but now we also need to output all of these numbers so we can actually have the counts and the sums for these gender choices for us to then have to be able to compute the averages afterwards. To do this, we will define our output type, which is our generated sum output. So we just create our struct where we insert all of the values for it. So the reason I'm getting an error here is because I'm not returning what our function is actually expecting us to return. So I just need to change it. We now have a computation which is actually going to compile. We are now outputting something different than our salary earlier, our sum average. So for us to actually understand that when it is outputted and added to the contract state, we need a way to have a public representation of the output. Because what is actually outputted is the secret type, but then that is recombined back into our public types. What we need to do is actually create a public representation of the result.
So we need to publicize something about our survey here of the average salary. And we have decided that we would like to publicize the average of each gender salary.
Exactly.
And that's what we need to define. Otherwise, it would be a jumble of numbers we've asked it to just do, right? And would just be some bytes we would get that would be non-necessarily translatable unless you understood what the recipe was. So we're just trying to combine that into something that actually makes it when looking at it.
So what we're going to do is we're going to have just a public representation of all of the types. Once again, just defined at the top. Yeah, the public representation of what we have in our ZK compute file. You can see the only difference is the secret binary integer versus our integer with I32.
Which goes back to the point that we often recommend that you actually do use the same structs in both the public and non-public part if they're not giving away any of your secret data or secret input, simply because the struct just make more sense, and these are not underlined anywhere. The contracts are not readable as is when you deploy them to the contract.
And it also doesn't matter because this representation is just for us to actually read the outputs of the computation, which is already going to be public when we open it. So that is still allowed, but it's not going to reveal anything about the inputs that we're giving. Now I'm also just going to add one more struct, which is just going to be our result that we're going to save in the state. So instead of just having an U32, I am going to have our generated averages used here. It is just 3 values of I32. We're using.
So it's just 3 numbers.
So that's very neat.
So they're awesome numbers.
Yeah, they're awesome numbers. Good. What would we need to do now to actually have all of this work? Well, first off, we need, this is still the same. It's going to output the same. However, here, when we are opening the values, we are not just opening the U32 anymore, because the open value is going to give us our secret variable. And then we now need to deserialize it into a known struct, which we can then use. To do that, we have to change the read variable we have right here. So we can actually read our gendered result instead. We would like to have our gendered sum result as our output. So how do we do that? Well, we can actually we can actually use the types we have defined to help us. We're just going to add the ZK state, sorry about that.
And maybe we should go through the line by line.
Yeah, exactly.
So what you're doing here is shaping up how to represent the data, how to actually grab the secret data from the nodes and showcase it in the state.
Yeah, exactly. What is actually happening here is that we are opening a variable. So that is our result we are opening. We are getting all of the secret variables IDs. We can open more than one variable. So this can also be used for other cases, but in our case, we are only opening one variable. Every computation is going to open one variable for us. And that's why we also have this assert. But what we're going to do is we're going to get the open variable, and now we're going to read this open variable with the current function. So what this does is we are getting the variable from our zero knowledge state. That's the secret part of the state. That's the one that says, oh, we have an open variable here. Here is all of the values you need. We're going to take the data, we're going to clone it, and we're going to unwrap it. So now we end up with a byte array. And this byte array, we can now use the state read from for our gendered sum result, which would then leave us with our result. Oh yeah, I just need to import it. Now we have our result here, but our result is not an average. Right now we are outputting all of the sums and all of the counts. So we need to change, we actually need to create the averages. What we're going to do is, instead of making this computation right here, which is just a normal average, we're actually going to just quickly delete it. And now we're going to create our averages. What we can see here is that we are just taking our gendered averages and creating an instance of it where we are computing each average salary for each gender. But see, I have defined a specific function here that ignores the cases where there are no inputs for our average salary. So we are trying to divide by 0.
So it's to make sure we don't crash the servers, basically.
Because division by 0 is not a great.
It's not a great thing to know the database.
I just made a little easy function, which is just division where we ignore 0, where we have our numerator, which is an I32, and our denominator, which is an I32. And if our denominator is 0, well, then we just return 0. But if not, we do normal division. So
we do the math needed to create an average.
Exactly.
And why do we do the average calculation out here? It might be more logical for me to think we should do that in the zero knowledge computation.
Since we are actually sending in our gender in secret, all of the inputs genders are still in secret. So as long as we have a high enough amount of inputs for the different genders, these will actually conceal each other, and therefore we cannot tell anything about who gave what as an input. We can, however, say that we know the amount of one gender there is in a company. Yeah.
And sometimes we don't need to do a secret action inside the secret part of it if we can just eliminate the trace of the data itself. So yeah, the last part is
just actually setting our result. So here we're actually using the averages we just calculated. We are setting our state to actually contain these. We are also just getting the number of employees, which is unnecessary, so we're going to delete that. And then we are telling the contract, you are now done. And also, this is where you would just change it to not be done if you wanted to do a computation again sometimes later. However, the nodes are still allocated for you, and you are paying fees when they are allocated for you.
Yes.
Because they are actively protecting your secrets.
Now the fun part comes. So just to iterate what we've been through for now, we've done the petition learning challenge to just show how easy it was to do anything. Now we've taken it to the zero knowledge part, and we did the first thing, which was increment the amount of inputs we got from a company to see how many people actually sent any things into the contract. And we've deployed that to the testnet as well. Now we're doing the third part of the challenge, which is to work with the secret data in a more in-depth way without giving away any of the knowledge behind it. So what we're trying to achieve is actually deploy the contract to the testnet. Again, we've made a lot of code changes. Now we want to check, does it actually work on the testnet? Does it work on Partisia blockchain as it is? And it seems that it should work right now.
It should work. Yeah.
So we've deployed it. We can see our state is here. The number of employees is still 0. Now we've had the new contract out there. So this is the first deployable contract. I'll share the link as well. And then we can start inputting different pieces to it if we want to. If you have any access to do any interactions, feel free to go to the browser, click on the interact button, click on the add salary, and then add a salary. I'll do it as well.
And remember, the gender choice is 1 for male, 2 for female, 3 for other.
And my salary as well, so we should be able to see some inputs.
Already 2 people. Guess who that is? But added our salary.
So I think it's a great showcase of how to compute things. Yeah. Hey, so if you want to do anything from the hackathon or get access to us in general, Jens and I are available on Discord and all the dev support channels, or raise the tickets if it's personalized that you need to ask any questions. It's been a blast making this hackathon workshop, and if we get a lot of positive feedback, we might do more. Have a really good day.
Awesome. So thank you so much to Mikey and Jens to walk us through how you create your first, multi-party computation Rust contracts. So a little bit of Partisia, because I haven't really presented where I work and who all of these incredible people that have been working on multi-party computation for so many years are. So where did the whole idea of Partisia blockchain come from, and where does our love for multi-party computation come? And that is from Ivan Damgaard, who actually wrote the first papers on MPC and as an incredible cryptographer from Denmark, and that is where Partisia is from. And so, we've had incredible researchers from Peter and Kurt and all of our founders who have been working continuously to basically bring MPC to, the public. We've been, on the private side of things, just doing a lot of research for a really long time. And it's really around 2021, 2022, where we only really kind of took the project out to the public. And so today I'm here trying to really get devs excited about coming to build with multi-party computation, because it's just a field of knowledge where I think is gonna rapidly increase how people view how data privacy is a really, really important thing, specifically in the world of AI, where it's just gonna become a currency, in my opinion. So yeah. Please check out Partisia. We'll probably add links on the GitHub repository where we just talked about through the workshop, and also to our documentation and everything. And now I would, I just gave the summary. And now I guess I would just like to give thank you for inviting me today to speak. And I would also open kind of the floor for any questions you might have.
So I guess one of the things I've always thought about with combining TEE and MPC, obviously, like you said, there's the synergies. One that, working in a TEE project, I've always thought about hardening the TEE model, using MPC to make, shore up the vulnerabilities of cracking hardware, right?
Yeah.
And then, of course, I think about collusion resistance for the MPC side. What have you thought about that? What would a model look like for you to use MPC at consensus layer on a TEE network? Say if we were to integrate MPC in secret network, just the layer one, to harden the validator models. What would that look like? How feasible?
Yeah, I think it's completely feasible. I think that's why we are here talking to each other. I believe it's still a place where it needs a little bit of research, because obviously each networking has taken either TEE or MPC to their own. One of the things that MPC can do is secret sharing, specifically so that there is no point where a secret is from one specific user and what I'm saying is from a specific TEE. So those are always shared, and you can't know when something has been kind of vulnerable or kind of hit by an attack, because some of the nodes will basically not have the same answer as some of the other nodes in our MPC networks. Obviously, this is all working in a completely encrypted manner. So it can really make robust to basically make sure that not a single validator, I don't know specifically how fully secret network works. I know more from the theoretical point of view of how maybe a TEE network would work. But I guess from the validator side, obviously you have attestation with TEEs, and normally that would just explain to you that they've done work in a proper manner. I guess that, albeit really hard, could be, attacked in some ways. I think MPC can really help there to make sure hey, actually, this is not true what they're saying, because I know that inside there's been this and this and that actually don't really kind of make sense to what my other nodes are telling me, like the MPC nodes are telling me, if that makes sense.
Yeah, one of the things that was kind of talked about, it was actually a couple of years ago, was using MPC to break basically the validator keys, which on Secret Network, the key lives inside the TEE. So theoretically, if you were to crack the TEE, you could gain access to that key, which not even the validators know.
Yeah.
But if you were able to crack it, you could get that. Now, if you were able to use an MPC model to break that key into multiple, you would have to sit there and break every party's keys, making it almost impossible.
Exactly. So that's exactly what would work with the secret sharing I was saying. So it's like every one of these secrets from the validators would just be divided on those blinded shares that we were talking before on how they would connect between each other. And each blinded share would probably live on a TEE. So in a TEE, you would maybe have like a number of blinded shares, but no TEE would have any specific secret.
One would have it.
Yeah.
Yeah. Okay.
That works, for example. Yeah. I think it's a space of research, so it's kind of pretty cool to just think about different ideas. I mean, there has been people that have already put systems with MPC and TEE together. But I think it's interesting to work on networks that each one have their expertise and kind of combining them together. I think that's like just really cool. Yeah.
Yeah, I like the idea of using each one's strengths to kind of balance out the other's weaknesses.
Yeah. Some of our things to take some time to compute.
Yeah. So TEE can add that speed to
exactly,
and then MPC can add like a strengthening to the TEE model.
Yeah. I guess if anyone else has no other questions, I guess we can close it off here. And again, thank you so much for having me. It was awesome to just talk about, I guess, one of my passions. And share it to everyone. And I encourage people to start trying out like writing Rust contrasts and looking at Partisia and MPC.
Thank you.
Thank you.